Assalamu alaikum. Before knowing the details of this lecture, I would like you to start by stretching up your mind and think for a moment with me. So imagine you have two different cases, two different soils. You have soil A and soil B. These soils have blends, exactly the same blends. They were irrigated with the same amount and quality of water. They were nourished with the same amount and types of fertilizers. They were growing at the same time, but they were growing in two different types of soil. Now think with me. Why one side of the blend died? Why the blend in case B died? Can you think of a reason? You have your time now. Alright, I think this is enough time, and I'm gonna tell you the answer. You should know it and figure it out by the end of this lecture. So let's get started. Alright, in today's lecture we're gonna learn a lot of fantastic things that will make you really an expert in the soil and know more about it. So we will try together to answer the question, where does the charges in the soil comes from? We're going to know together the concept of cation exchange capacity and how that is implemented to the nutrient and the water holding capacity and controlling of chemical transport in the soil. We're going to learn about the factors that affect the cation exchange capacity. We're going to know how to determine and measure cation exchange capacity of the soil in the field or in the lab, and also with some equations. Then we're going to learn about base saturation, and then we're going to discover together other types of colloids. As you remember from the previous lecture, we have crystalline clays, and then we have other types of colloids, which basically are the aluminum and iron oxide or organic colloids. And finally, we're going to see the relation how soil pH is related to the concepts of charges and cation exchange capacity, and how the soil pH is going to affect the nutrient bioavailability. I'm sure that through the last lecture we've been wondering, where does the charges comes in the soil? Because we've seen the importance of the charges, we've seen how the soil with the charges can control and hold the nutrients, holds water, and also control the movement of pollutant in the soil, and we've seen the implication of this. But now I think it's the right time to answer, where does these charges come from? When we talk about clays and we talk about colloids in general, there are basically two sources of charges. One of them is called isomorphic substitution, which is basically a permanent source, and the second type is called pH dependent charge, which means it's a variable depending on the pH. Now, let's give more details on isomorphic substitution. Basically, isomorphic substitution is considered as the largest source of charges in most of the clays. And this is specifically very common for 2-to-1 types of clays like vermiculite, illite, and other types like chlorite and other types. And they result in negative charges. However, the pH dependent charges, as we said, it's a variable depending on the condition of the pH. And this kind of charges is more common for 1-to-1 clay like kaolinite, and it's also very common for aluminum and iron oxide and humus. Now the thing that with this type of charge, it's not permanent. So it means that with the pH increase or decrease, it can lead up to positive or negative charges, and you would see that in more details with the coming slide. To understand the concept of isomorphic substitution, I want you to go back with your memory and look back at the main structure of the colloid. You remember, colloids basically, or clays like the crystalline clays, are basically formed from tetrahedrons and octahedrons. Now you remember what exactly exists in the tetrahedron? The tetrahedron, which basically looks like a pyramid, has silicon at its center, while the octahedron looks like two pyramids put together from the base and have aluminum at its center. Now what's going on with isomorphic substitution? Isomorphic substitution, it means that as the soil undergo the process of weathering, like the disintegration and also the chemical weathering with water and other things, what happens that the central atoms like the silicon in the tetrahedron can be replaced by something else. And in this case, it can be replaced by a cation that has exactly the same size but less charge. If in the case of tetrahedron, it can be, for example, aluminum. So aluminum would change the silicon at the center and it would fit right away there without changing the structure, without changing the tetrahedron. And because of this exchange, you would end up with unsatisfied charges, I mean with the oxygen that are in the tetrahedron. And that at the end of the day would result in more negative charges. The same condition for octahedron, that undergoing weathering condition, the central atom like aluminum can be replaced by something with the same charge but with a lower charge but the same size. And in this condition like the magnesium. So when magnesium replaces aluminum, it fits very well in the center because it's the same size and the structure will not change, but at the end of the day it will end up with more negative charges because now you replace it with something with +2, whereas in the past it used to be 3+. And it means that there will be OH or oxygen unsatisfied charges, and it will end up to increase the negative charges. And you would see this more in details in the coming slides. But in general, it can happen at the level of the tetrahedron and the octahedron. Then remember that we said that the tetrahedrons, when they put together, they form sheet. So the same process can happen at the sheet level or at the layer level or at the clay level itself. So in case of the tetrahedral layer or tetrahedral sheets, you can have a replacement, or aluminum can be, aluminum and iron can replace for silicon. And in the octahedral sheet, where you have aluminum at the center of the tetrahedrons inside the tetrahedral layer, it can be replaced by something with the same size but lower charges like iron, like magnesium, or like zinc. As you would see that all of them are now 2+2+2+. And that at the end of the day would result in a more net negative charges, and that would also means that those negative charges in the soil should be occupied by something. It means it will absorb other nutrients in the soil, and that will end later on to concept of cation exchange capacity. Let's have some fun together and look how the isomorphic substitution leads to increase the charges in the soil. Again, I'm emphasizing that this exchange of the central atoms happens with weathering, because you know these atoms are like the silicon are really attached in the center of the tetrahedrons, so you cannot remove it like this easily. You need force that removes it, and this force comes with the weathering. When you disintegrate it or break down the soil into smaller and smaller particles, and with the chemical weathering, things can be added and diluted and so on, and that's when this exchange happens. So what would happen now if we exchange the silicon in the tetrahedron with aluminum, which is basically 3+? What would happen? So we see now. And what would be the net negative charge? Think for a moment. Okay, let's see it now together. Well, basically what will happen that when you replace the silicon, which is 4+, with aluminum, which is 3+, it's the same size but a lower charge, it ends up with unbalanced negative charge. So by this replacement, you remember each one of the oxygen is basically -2. So at the end of the day, when you replace it with aluminum, it basically can attract, still attract to 4 oxygen atoms, but it will end up with negative charge, 1 negative charge. Now what would happen if weathering undergoing, and the silicon is exchanged by magnesium, which is 2 plus. Same size almost, but much lower charge by 2 times. What would happen? Basically, it will end up with more negative charges. It will end up with -2. Why? Because now this is only 2 plus. It means that it would only can hold 2 oxygens, and at the end of the day you will end up with more negative unsatisfied charges. And you can get more details with this like illustration by clicking on the link below. But I guess now, as I said, that this process, isomorphic substitutions, requires that you change the central atoms or the central element at the center of the tetrahedron or the octahedron with something that have an equivalent size, almost the same size, but a lower charge, and at the end of the day it end up with increasing the negative charge. So if you look at the table up here, you would see that at the tetrahedral sheet, okay, you would see that if you look here, you would see that silicon and aluminum and iron, they are almost the same size. Although like aluminum is a little bit larger than silicon, or iron is also larger a little bit than the silicon, but it's almost the same size, but a little bit slight different. But it can fit at the center of the tetrahedron without changing the structure, but it end up with increasing the negative charge. Now, if you look at the octahedral sheet or octahedrons, what happens that aluminum can be replaced with anything that is smaller charge. And in this case, if you look at the arrows here, you would see that it can be replaced by magnesium, by zinc, or by iron. And all of these would result in increasing the negative charges. Now, things again, I'm emphasizing that if you look at the figure here down, that it might happen at the tetrahedron and octahedron levels, but also it can happen at the sheet level and at the layer level. So anything that in the, like, it means that it will happen like a replacement of the central atoms of the tetrahedron at the sheet level, for example, can result in increasing the negative charges and so on. It can happen also at the interlayer space between for example between the layers. In case like here, what you see, this is a 2-to-1 clay type, and as you can see, things can happen also exchange at between the layers, because you have also tetrahedron and tetrahedral sheets. However, when we talk about the second type of charges, which is a pH dependent charge, is completely different than the isomorphic substitution or the isomorphs, because pH dependent charge is a variable and it is not a permanent source of charges like what happened with the isomorphic substitution. In the isomorphic substitution, due to weathering process and the exchange of the central atoms, you end up with changing in the structure in the central atoms that exist in the tetrahedron, and that will create charges that are fixed. In the condition of a pH dependent charge, is what is happening there, it depends on the pH. If the pH increase, like, you generate positive charges. If the pH decrease, you generate negative charges. So you see that it depends on the pH to create negative or positive charges. And emphasizing that the pH dependent charges mostly commonly happened in 1-to-1 types clay like kaolinite. It happens also in aluminum and iron oxides, colloids, and also it happens in the organic colloids. So what you would see that as I said, that depending on the pH, you will create positive or negative charge. Something else I want to emphasize about the pH dependent charge, that it happens at the edges. At the edges, what do we mean by the edges? Let's look at the things here down at this chart. So if you, this one here shows the octahedron. If you look at the center, you would find that you have a medium pH, and under a medium pH you have aluminum at the center of the octahedron, and to the edges you have hydroxide, for example, OH. Now, what happens with the increase or decrease of pH? Well, I want you first to look at the picture here to the right, that in the soil you have two things. You have, as you see in the picture, you have the soil particles, and in the soil particles we call the adsorbed sides because there you have the negative charges, and then you can have some of the cations are attached to the soil, they are adsorbed. So like you see here hydrogen, you see other types like potassium, sodium, magnesium, nutrients are adsorbed to the soil. And you have also some of them non-adsorbed, they are free in the soil solution. So what happens then with the pH here and the octahedron, for example? In this condition, that as the pH increase, what happens that when the pH increase, the concentration of the hydrogen in the soil solution decrease. And as it decreases, what happens to the OH that are attached to the octahedron? It will dissociate into oxygen and hydrogen. The hydrogen will go to the soil solution and the oxygen will still fix there, and that will end up with creating negative charges, more negative charges, because now it will be from OH, which has a net negative charge of -1, to oxygen, which has a negative charges of -2. That would increase the negative charges. However, the opposite would happen as the pH goes down. When the pH goes down, it means that the concentration of hydrogen increases. And when the concentration of hydrogen increases in the soil solution, you have a lot of hydrogen here, and therefore those hydrogens will go and will be where it will protonation. Protonation will happen. That means this H will link with the OH that are in the octahedron, and that will end up with creating net positive charges. So you'd see that if the pH is high in the soil, it will create a net negative charges because deprotonation happens. It means that the hydroxide will dissociate and the hydrogen will go into the soil solution, and then you end up with oxygen on the octahedron edges, and that will eventually increase the net negative charges. However, when the pH goes down, the protonation happens because you have a lot of hydrogen in the soil solution, and then hydrogen will bind to the hydroxide, and that will create more positive charges in the soil. To give you more illustration about the difference between the isomorphic substitution and the pH dependent, if you look to the right here, that the isomorphics are permanent source of charges, because the exchange of this process happens with the weathering, and it will actually, the charges will be generated by replacing the central atoms of the tetrahedron and the octahedron by something or by other cations that have same size but almost lower charges. For the pH dependent, it happens at the edges, and depending on the pH condition, whether it's high or low, it will create either positive charges or negative charges. Now I want to ask you another question. Well, can I know the stage of weathering by looking at the soil type? I mean, the clay type. I mean, if I find, for example, kaolinite in the soil, or if I find aluminum or iron oxide, can I say that the soil is more mature? Or if I find, for example, fine grain mica or primary minerals, can I say whether the soil is mature or it's still young soil? To answer this, let's see the following example of illustration here. If you look at this figure, you would see to the left side you have primary minerals and different types of primary minerals. And if you look to the right, you would see that you have
if you move from the left to the right, you would see different types of clay minerals that we know as 2-to-1 until it forms at the end aluminum and iron oxide. And you would see up here that the condition here, you have hot, wet climate, which means very intensive weathering and rapid weathering process. So what is going on here? Well, basically, if the soil undergo weathering, physical and chemical weathering, it will change in the size, but also chemical weathering would change its structure, and it will end up to the formation of new types of minerals. It will form from a primary minerals to a secondary minerals. And in this condition, if we just trace and look at the muscovite here, which is very rich, a primary mineral, very rich with potassium. As it undergo weathering, you would see here in the arrow that minus K means, minus sign here means losing. So undergoing this weathering, it will disintegrate in the size and also chemically will be altered to fine grained mica. And during this alteration, it basically lost some of its potassium. And if the weathering undergoes again, you will lose more and more potassium, and that will end up with a smegtite, or what we know it as montmorillonite. Again, weathering would continue and the time would continue, and the soil would lose more and more things from it, like silicon. And as it loses the silicon, its structure completely will change, and its type completely will change from 2-to-1 type of clay minerals that we know that it has a huge surface area, huge number of charges, swelling type clay, to kaolinite, 1-to-1 soil, which is basically, we know it, a non-plastic, lower surface area, it's non-swelling clay, and so on and so on. And again, if it undergoes weathering and the weathering continues, the kaolinite can lose silicon, and as it loses silicon, it will end up with aluminum and iron oxide. So the answer to this question, yes, you can know the stage of weathering and you can judge the maturity of the soil depending on the types of the minerals that exist in the soil. So if you have a soil that have primary minerals, then you would judge to it as it just a young soil. But if you see, for example, you have any types of these clays like fine grained mica, vermiculite, or chlorite, it will indicate that this soil is in the like early stages of weathering with these types of clay. But if you see smegtite, then it's an indication of intermediate. And if you see, for example, kaolinite, it means it's advancing again. And if you see aluminum and iron oxide, it means that you reached a very advanced stage. The structure here is like it's already non-crystalline. There's no structure, whereas it's not crystalline structure, and it means that your soil is really very, very mature. And you will not form aluminum and iron oxide in the soil unless you have very intensive weathering that has been like going on for a longer and longer time. These kind of differences, you might find it from one place to another place depending on the weathering intensity, and you might also find it within the same soil profile. For example, at the top soil, the mineral content might be different and the maturity might be different than the down or the deeper part of the soil profile, and this can indicate the development of the soil. So clay type can tell us about the development of. We've seen from the previous weeks that the importance of the surface area to the adsorption. We've seen that larger surface areas means you absorb more nutrient, water, control the pollutant more than the soil with a lower surface area. But what I want you to think about now is that, is it always true that the larger surface area means more negative charge in the soil and therefore holding more water, nutrient, and contaminant? All this case can be violated a little bit. To answer this question, let's look down at the table here. This table shows you different types of colloids, whether it's like smectite, vermiculite, and so on. It shows you also the type of this colloid, whether it's a 2-to-1 and 1-to-1 silicates or other types of colloids like aluminum iron oxide or organic. It shows you the size, the shape, in the surface area. Some of them have internal and external surface area, some of them not, and the interplay spacing and the negative charges. If we start by looking at Smigtite, which is 2-to-1 crystalline silicate clay, and it looks like flakes. If you focus on its surface area and negative charges, you will find that this Smigtite, which is also called montmorillonite, has internal and external surface area. Its external surface area between 80 to 150 meters square per gram, and its internal surface area between 550 to 650 meters square per gram. If you look at its net negative charges, you'll find it's about minus 80 to minus 150. Now, if you compare this clay with another 2-to-1 silicate clay like vermiculite, you would find that it's a little bit different in the shape, in the size. And if you look at its surface area, you would find that its external surface area, I mean, is less than the external surface area of Smigtite. It's between 70 to 120, and its internal surface area between 600 to 700. However, if we just want to compare the total surface area in these soils and count for Smigtite, let's add, for example, the external and internal. Let's say use the maximum, 150 plus 650, that would be equal to 100 meters square per gram. For vermiculite, it will be 120 plus 700, that will be 820 meters square per gram. So vermiculite has higher surface area in total. Now let's look at its total negative charges. Its total net negative charges is also much higher than the Smigtite. And if we look at another type of clay like colonite, which is 1-to-1 silicate clay, it looks like hexagonal crystal structures, and if you look at its surface area, you would find that it has between 5 to 30 meters square per gram, much lesser surface area than the surface area of the 2-to-1 clays like Smigtite and vermiculite, and its charge is also much lesser than vermiculite and Smigtite. So we can say that in general, the higher the surface area, you will end up with a more negative charge. But this case is not always true, because if you look, for example, at the example here between fine mica and chlorite, you would find that for fine mica, the total surface area here is about 175, whereas for chlorite is 100, but their net negative charges is almost the same. So it's not always true, but in general, larger surface area means larger number of charge. If we also compare it with humus, which is organic type of clay, you will find that its surface area is variable, but it has also huge negative charges. Now, charges, the surface area, what is so great about this and how this is related to ion exchange? Well, if you have more charges and more surface area in your soil, it means you have more ability to control and absorb a lot of things in that soil. So, for example, you can have a more control of pollutant transport. If, for example, let's say a tanker of oil spill on the soil, and that soil has a higher surface area and a higher negative charges, that this oil and this contaminant can be just absorbed to the soil, and that would control its movement to groundwater, and hence you will protect the groundwater. But if you have a soil with a lower surface area and with the lower charges, it means that once this pollutant is added to the soil, it will find its way easily to the groundwater and contaminate the groundwater. It's something to remember that if the contaminant reaches groundwater, it will be extremely hard to remove it, very expensive, and almost very difficult. So you will end up with contaminating that water and the soil for a longer term and losing that water. It also affects the holding of the water. Now we have different soil types that have different number of surface areas and charges, and because of these differences, it will determine whether the water will be held for a longer time in the soil or just can be lost very easily, like drain out from the soil. Remember that if you have a soil and you grow plants on it and you add also fertilizers, and this soil is like always losing the nutrient, is not able to hold the nutrient and not able to hold the water, then it means that you have to add more nutrient and more water to that soil in order to make your plant living. That's why ion exchange and the concept of these adsorption and the charge is very important in the. And since they are very important, we have also to study how the nutrients are basically released from the soil to the plant. Let's say that if your soil have a good amount of negative charges, and then you basically add nutrient and fertilizers and water to that soil, it will be retained in the soil and it will be less removed or leached from the soil. But how these nutrients then can move from the soil all the way to plant? To understand this, we have to understand the concept of cation exchange, and then the cation exchange capacity. Well, cations are those ions which carry positive charges. But what is cation exchange? Cation exchange is the process by which a cation in the soil solution can be exchanged with another cation in the soil, or a cation in the organic matter can be exchanged from the organic matter to the soil solution, or from the soil to be absorbed in the soil or to be released in the soil solution. The cation exchange capacity looks at the things at a whole. If you look at the picture here, you would see that this clay has negative charges, but it attached to, or a lot of other cations, nutrients are attached to the soil. So the cation exchange capacity look at all of these ones, how all of them can be exchanged from the soil to the soil solution, or from the soil solution to the plant. So it will look at the process at a whole, at a given. Now, how this process of cation exchange works in the soil. First of all, I want you to remember that the isomorphic substitution and the pH dependent creates the negative charges in the soil. After the process of weathering, you end up with a soil that has a certain number of negative charges, fixed numbers. Let's say that it has 20 charges negative on it. Now, these negative charges in the soil must be satisfied, and therefore it must adsorb something that are positive, so it will be in a calm situation. Now, if you look here at the soil, you have the soil particles, and the blue part you have the soil solution. This soil, let's say, have, again, as I said, 20 negative charges. So these negative charges must be satisfied by adsorbing cations. Those are the positive ones. So some of these cations would be adsorbing the soil, satisfying these negative charges, while others still will be like excess existing in the soil solution. What happens that with the exchange, that some of the cations that exist in the soil solution will kick out some of the cations that are adsorbed in the soil, replace them. And this process of kicking out cations from the adsorbed or exchangeable side is called the cation exchange capacity. It basically measured as centimole of unbalanced charges. So that's the unit, centimole. and it can be expressed as positive charges adsorbed per unit mass, because remember, with the cation exchange capacity we are dealing with the cations, those who have positive charges. Let me give you the following example to make this point very clear to you. Look down here, you find that you have soil, and this soil has a certain number of negative charges. You can know the amount of negative charges by counting the number of dashes that it has. They are basically, you find them, they are 10. If I ask you a question now, how many hydrogen ions this soil can hold? And the hint is in the number of negative charges. You would say that after thinking that, well, since this soil has 10 negative charges on it, okay, and I know that hydrogen is +1, so these negative charges must be fully satisfied, and therefore you would need 10 hydrogen ions. In this case, we can say that this soil basically has a CEC of 10 centimole per kilogram, and therefore it can adsorb cations that have +1 charge, like it can adsorb 10 of them, like the hydrogen, for example, or like sodium, for example. However, if I change and I ask you now how many calcium can hold, then you have to think about it. Now, calcium is 2+, and to satisfy all the negative charges in the soil, you don't need 10. You only need 5, because calcium is 2+. And you would see that in this condition of exchange, the most important thing to consider here is the amount, is basically the number of the charges that the soil has, and not the number of ions that exist in the soil, because at the end of the day, that soil must satisfy its negative charges, the number of negative charges, and therefore it will adsorb to it exactly the same number of, it will adsorb to it a certain number of ions to satisfy that charge. If that ion has 2+, then it will be less than in case of having an ion with +1. All right, let me give you more example. If I ask you in this condition here, you have two different soils, soil A and soil B, and if I ask you the question, which one of these soils would hold more nutrients? And you would say that basically it's soil A. Why? Because soil A has more CEC than soil B. Now let's think together. We know that in the soil we have different types of cations exist. However, which one of these cations will have the priority and will have the strength to be tightly adsorbed to the soil among the others? And to understand this concept, we basically have two different factors. The first factor is the strength of adsorption. And the strength of adsorption is controlled by the valence of the cation and by the hydrated radius of that cation. We know that the soil have negative charges, and these negative charges must be occupied by positive. In the condition that we have two different cations, one of them is +1 and another one is 2+. Which one of them will be tightly held in the soil if the soil have only two negative charges? Think about it for a moment. You would find that the one with 2+ would be tightly held in the soil. Why? Because that one has like more positive charges, and the soil has two negative charges, and therefore like it will go and fit in the adsorption side, and it will be very hard for the one with +1 to kick it out, because it's like having two hands holding two hands in the soil. So very difficult to be removed by like a one with a smaller muscles like the +1. The second factor is the hydrated radius. Now imagine that you have the same number of negative charges in the soil, only two, but you have two different cations that have exactly the same number of charges. Both of them are +1, +1. However, one of them have a larger hydrated radius, meaning that this cation is surrounded by a larger shell of water, and another one with a smaller shell of water radius. Which one will be tightly adsorbed in the soil? You would find from the picture that the one with a smaller hydrated radius is the one tightly adsorbed in the soil. Why? Because as the hydrated radius increase, it means that this shell of water will basically dilute the strength of that positivity, and therefore it will be like not that strongly positive, and therefore the one with a smaller hydrated radius would have more affinity to be held tightly, because its positivity is stronger than the other one, and therefore it will be tightly attached in the soil. Things to remember here that the strength of adsorption of a cation can be measured by using this equation. It's basically the valence over the hydrated radius. And as you can see from this example, that the smaller the hydrated radius and the larger the charge, the strength will be much larger and stronger, compared to another cation that has a larger hydrated radius and smaller charge. The second factor that can control the exchange of cations is the prevalence of the concentration, dominancy of the concentration of a particular cation in the solution. Now, again, we use the same example of soil, that your soil have like this number of negative charges, and these negative charges has to be occupied. In this condition, you have two different cations exist in the soil. One of them is 2+, and the other one is +1. However, the concentration of their existence is different. The one with 1+ exists in much higher concentration than the 2+. Now, which one will be dominant in the adsorption side of the soil? It's basically the one with a higher concentration. Why? Because this one, the larger the concentration of the ion, regardless of its charge, regardless of its strength, it will basically kick out the smaller number of the cations, even if they are having higher charges. It's, you know, like what? It's like saying that it's like fighting. It's like fighting. Imagine like you have one guy with a very strong muscles that sitting on the chair. If you want to remove him alone and you have just small muscles, you won't be able to do it because he will beat you. However, if you bring a group of like students, the whole class for that person, and he will be afraid, and then he will be easily kicked out from the chair and removed. Exactly the same thing is happening with the soil. And based on the law of strength of adsorption, which is affected by the valence and the hydrated radiance, we can now sort out, or we can now list the strength of adsorption for all the cations that exist in the soil in something called Liotropic series. Basically, in Liotropic series, you would find that you have hydrogen, aluminum, calcium, magnesium, ammonium, potassium, and sodium. And as you can see that if you move to the left, you basically, these ones who exist to the left, they are having a higher strength, and therefore they will be held more strongly in the soil, in the adsorption side, in the exchangeable side, than the one to the right here. And you would see that hydrogen is almost equivalent or stronger than the aluminum. Why? It's not only about, again, to remember here, it's not only about the number of charge, but remember we apply now the concept of strength would depend, which is basically the valence over the hydrated radius. So by this concept, then you would see that hydrogen is almost equivalent or largely held in the soil than aluminum, and both of them will be tightly held than calcium, and then magnesium, and then any other down here. However, if you look at magnesium will be held more than the ammonium, and so on and so on. If you look at potassium and sodium, they will be almost held in the same way. So if they exist in the same concentration, all of them, then hydrogen will win, and it will be the only one in it will kick out all the other type of cations here, and it will be the only one exist in the exchangeable cations. However, if the concentration of anyone here from the right side of this series exists in a higher concentration, like if sodium is very weak in the aleotropic series, but if it exists in a very concentrated solution, then it can be dominant in the exchangeable side. It can exist in the exchangeable side, and it can kick out hydrogen if it exists in a smaller concentration. And if I ask you a question, what determines the total amount of CEC that the soil have, and therefore the amount of cations, water, and pollutant that can be adsorbed and exchanged in a soil? You would find the answer to that basically two different factors. The first one is the amount of clay and organic matter. Why? Because we've seen that clay and organic matter have a lot of negative charges. So if in your soil you have more clay and you add more organic matter, that would end up to increase the total CEC in that soil. The other example, or the other factor, is the type of clay minerals that exist. And we've seen, as you see in the picture, that different clays minerals, like the crystalline or non-crystalline minerals, holds different amount of net negative charges. So if you have in your soil like a huge percentage of vermiculite, then it will end up with increasing the amount of negative charges in your soil, and therefore the CEC. Same if you compare it to your soil have a lot of kaolinite, then that would decrease the amount of CEC that exists. It's great that now we know a lot about CEC and it's important to the soil, but is there any way that we can use in the lab or a technique so we can come up with the exact number of cation exchange capacity or the number of charge in the soil? Well, yes, we can do that, and the following picture illustrates for you that experiment. So you have here 4 different beakers, A, B, C, D, and you can see you have funnels and you have also some things here side. So if you just look at A, imagine that now you brought a soil and you put it in this beaker, and since you know that that particular soil have different amount or different cations that can be adsorbed in the soil, and some of them are in the soil solution. So the first step that we need to do to determine the CEC, that we need to remove all of these adsorbed cations from the soils. How can we remove them? We use the concept of exchange of ions. Remember, if we have something that is more concentrated, then we can kick out all the nutrients from this adsorbed soil, even if they have a larger charges or strength, or like more strength to be held. So in this experiment, we brought ammonium salt solution concentrated with ammonium, and then we use it to kick out all of the nutrients. So when you put it in the soil, you basically, the ammonium would replace all the cations that exist in the adsorbed side of the soil and will kick them out. And they will be, as you see in step B, there will be all of these cations will be kicked out to the soil solution, and therefore they will be leached out to the beaker. And what will be remaining in the soil? What will be remaining is only ammonium. It will be adsorbed to the soil, and some of them exist in the soil solution. The next step that we need to remove the excess ammonium, which are the ones who exist in the soil solution. And we can use, for example, alcohol, any solvent like alcohol, to remove them. After removing them, we only have ammonium adsorbed only to the soil. And since we know that ammonium is +1, so if we count the number of ammonium that exist in the soil, we know that each one of them is attached to a -1 in the soil. So by knowing the number of ammonium, that are adsorbed in the soil, we can know the number of charges. So how can we know the number? We cannot measure it in the soil, but we have to leach it out. So what we do in the next step, that in step C, we bring another concentrated solution that has the same charge, +1. And once we put it in the soil, it will kick out all the adsorbed ammonium in the soil to the soil solution, and therefore it will be later on leached to the beaker. Next step, what will happen, as you see in step D, that potassium will be exist in the soil, adsorb, and also in the soil solution, and we have all the ammonium which were at the beginning or which we were before previously adsorbed to the soil, they are now in the beaker. So we can now know the number of these ammoniums, know the concentration by using the instrument, and we can measure the concentration. So the concentration of this ammonium will be equivalent to the number of charges that exist. If the concentration, let's say, is 100, then we know that you have 100 charges in the soil, and like this. We can also estimate the amount of cation exchange capacity in the soil using equation. And as you can see from this equation, you only need the percentage of organic matter and clay to calculate the CEC, or to estimate the CEC. So if you have an example, if you have a soil that have a 30% clay, 50% sand, and 20% silt, and the amount of organic matter is 3%, what would be its cation exchange capacity? We can apply it in the equation. So CEC would equal to the percentage of clay, of organic matters times 200, plus the percentage of clay times 50, and that would be almost 21 centimole per kilogram in this soil. So that's the unit. Easy example, right? The concept of CEC, however, can be also used to calculate base saturation. Now, what is base saturation? Base saturation is basically, since we know that some of the cations are basic cations, they are alkaline. So we can determine their percentage in the soil, and this is called base saturation, which is basically the proportion of the basic cations occupying the exchange site. These basic cations like calcium, magnesium, potassium, sodium, and ammonium, all of them are very important to the soil, especially for the plant. Why? Because as you see, they are basically macronutrients, and macronutrients are needed in a higher amount in the soil. That's why we need to know how much macronutrient exists in the soil. If their amount is low, then we have to add fertilizers so we have more nutrient in the soil for the plant. So how can we do that? We can do that by this equation. So the base saturation is equal to the summation of all the basic cations divided by the CEC times 100. Alright, now we've reached the part of other types of soil colloids in the soil. As we said that we have crystalline silicate colloid, but we have other type of colloids like the aluminum and iron hydroxide, and those kind of colloids basically exist, and they are an indication of a very advanced weathering, and they have also a net negative charge, and they have also a net positive charge, and they are highly dependent on the pH, as we said in the previous slides. We've seen that aluminum and iron oxide are pH dependent, like their charges can be generated depending on the pH. So if like you have gypsite and geothite, if they present in the soil, they are an indication of maturity, but their charge is affected by the pH. So if you have a higher pH, at a higher pH, it will end up with deprotonation, and that will increase the negative charges. And at a lower pH, you have protonation, and that will increase this. The other type of soil colloids is the organic. Organic matters are also called humus, and humus basically the flexible or the stable fraction of the soil organic matter. What does it mean? That for the soil, when it is broken down with the weathering, the end stage, it will form iron and aluminum oxide. Same thing for organic matter. They also undergo decomposition, and the stable form for the organic colloid is called humus. Now focus, humus, not humus. It's not humus. Don't be hungry. All right, so this type of colloids are also non-crystalline. They are organic, and therefore you expect to have carbon and hydrogen and oxygen on it. And also and if you look at the structure of the humus, it looks like the picture you see here. So basically the humus having carbon, hydrogen and oxygen, and they are also basically dependent on the charges to generate its negative or positive charges. And if we want to see how it is basically dependent on charge, it exactly uses the same concept. So under a neutral pH condition like 7, you have it like neutral, no charges. However, if the pH increase, what happens? Similar idea to deprotonation, and it will end up to increase the net negative charges. At a lower pH, the same concept of protonation will happen, and it will end up with having higher positive charges. So the colloid or the organic colloid behave exactly in the same way like kaolinite or like aluminum and iron oxide when it comes to its source of charges. It's depending on the pH. Now we can see that the pH is very important to generate the charges, but the pH also is important even to the bioavailability of the nutrient to the plant. So the pH is basically, if we want to know more about it, it's basically an indication of the acidity or basicity of the soil. It's affected by the amount of hydrogen in hydroxide. So when the pH is very low, it means that you have much higher hydrogen, and therefore you have acidic condition. At a higher pH, you have more hydroxide, and this is basically a basic condition. And this is also related to the type of cations that exist. So you have some of the cations that are called basic cations, and other are called acidic cations. For the condition of acidic cations, when like aluminum, iron and hydrogen, when they exist in the soil in a large amount, and when water is added, they will be released in the soil solution, and their release will end up with decreasing the soil pH, making the soil very acidic. The basic cations act on the opposite manner. When calcium, magnesium, potassium and sodium exist in the soil and they react with water, they tend basically to decrease the acidity, and therefore increasing the basicity, and the pH will increase. So how this works and how it is related to the condition of the climate and the nature of the country or the nature of the soil, it basically follows the concept which I will explain now. If we talk about arid countries like Oman, most of the soil have a lot of calcium on it, adsorbed. So when rain happens and the calcium in the soil, what happens here, as you see in this equation, X indicates the clay particles. So calcium is adsorbed to the soil, but as it reacts with water and the water dissociate into H and OH, the hydrogen because the hydrogen has more strength, it will kick out the calcium. Remember the leurotropic series? It will kick out the calcium from the soil, from exchangeable site in the soil, and therefore it will be in the soil solution, and therefore what will happen, it will increase the OH. So this one can be understood from the following example down here. So in the case that in your soil, if your soil have a lot of calcium carbonate of it, when rain happens, the calcium carbonate dissociate into calcium and carbonate, and then the carbonate react with water to form bicarbonate and also release OH. And if this process continue again, it will still release more and more and more OH. So in the condition of a soil of Oman, when rains happens, it basically still making the soil becomes more basic and basic. That's why our soil is always having a higher pH. If you measure it, always more than 7.9 to 8 point something. However, if you look at the soils that exist in the forest, for example, in California, in Amazon, or any forest, where they have a lot of rain, and because of the weathering process and the weathering intensity, those soils always have aluminum hydroxide on it, as like indicating a very advanced weathering. So since you have a lot of aluminum and iron, and if we take the example of aluminum as it's one of the acidic cations, so when aluminum reacts with water, it ends up with forming aluminum hydroxide and releasing hydrogen in the soil. And as the process goes on, you would see that you still release more hydrogen and hydrogen. So if the hydrogen is higher in the soil solution, it means that the pH will be very low, and that's why these cations end up with decreasing the soil pH. The concept of soil pH is very important for the nutrient bioavailability. Why? Because depending on the pH, we can say that the nutrient can be bioavailable or not. Bioavailable means to be easily released to the plant and therefore can be absorbed. So in general, if you remember from the previous lectures, we have macronutrient and micronutrient, and the macronutrients are needed in a larger amounts like NPK, nitrogen, potassium, and phosphorus. They are needed in a larger amount for the plant growth. The micronutrients are needed in a small amount. So what happens with the pH, that usually the macronutrients tends to be bioavailable at a higher pH. So in the condition of Omani soil, where it is a basic soil, have a higher pH, we don't have any problem with the macronutrient. They are bioavailable. It means they can be absorbed by plants. Whereas for the condition of micronutrient, we really have a problem, because micronutrients tends to be unavailable in the acidic condition, as indicated by this graph here. You see that the arrows becomes very narrow. It means that becomes like less bioavailable. So in our condition, we have to add the micronutrients, adding them directly to the plant, because if we add a fertilizer with a lot of micronutrient in the soil, that will not work, because the pH is very high and this micronutrient will be not available to plant, and therefore they cannot absorb them, and therefore we end up with micronutrient deficiency in our plant. Therefore we have to use other techniques like the foliar, by which you add the nutrient directly to the leaf at a proper concentration, very low concentration. You have to calculate how much they should be added, and then the plant absorb them directly through their tissues, and then they can use it for the growth. If we look at the soil that exists in the forest, it's very acidic, and when the pH is very low, usually they tend to have a problem with the macronutrients. So the macronutrient in acidic soil is not available. That's why those people, like the people who live in the acidic soil, those people who have acidic soil, they have to deal with this problem by trying to control the pH, trying to increase the pH. So they add for example lime, calcium carbonate to the soil just to try to bring up the soil pH, and therefore making the macronutrients, which are very essential and needed in a larger quantity to the plant, they make them available to the plant. But they don't have any problem with micronutrient. That's why in their condition also they might have a problem with the micronutrient, because the micronutrients are bioavailable and the plant can absorb them like easily, and therefore like they absorb larger than the amount they need, and they tend up to get to like to be in toxicity problems. The pH is not only controlling the nutrient bioavailability, but also it's very important to make the condition favorable for the bacteria and for other soil animals. And remember, those soil animals like also and bacteria play a very important roles to fix, for example, nitrogen from the atmosphere to the soil and make it naturally available to the plant. And now, if somebody asks you a question, man, that if somebody observed that he has a deficiency of micronutrient in the soil, what would you advise him to do? I'm sure that you won't advise them to add micronutrient to the soil, because if they add it to the soil, they will be not available, and therefore you might advise him to add it as a foliar directly to the plant. So now it's very important to know that adding or dealing with fertilizers is not about only just adding the fertilizer to the soil. You have to have a knowledge about the soil pH, because that's very important to determine the bioavailability. And I guess by this now, I'm sure you would be able to answer this question, which I asked in the beginning of the lecture. So, what other possible reasons why the plant in soil B died? Probably it can be that soil B has, for example, a very low CEC, and therefore once you add the nutrient, they won't be absorbed in the soil and they will be easily leached out as you add water. And therefore, if you didn't add fertilizers more frequently, the plant have a deficiency. And not only that, because of the low CEC, if you irrigate like the same, because we are irrigating the same amount of water, the same quality, but soil A needs to be irrigated, for example, every 3 days, whereas in soil B, because it has a very low CEC and a lower surface area in their soil, it can lose the nutrient and the water easily, and therefore you have to add water more frequent. So that's all for this lecture. I hope you enjoyed it. Go back to the childhood. I think we all remember when we are playing with the clay to make different structures. And I hope that you enjoyed the chemistry, and now you know how the chemistry of soil is very important to many things and many functions in our life. Thank you very much.